Thanks very much, Sergey. Thanks very much for the introduction. And I think the title is absolutely, completely clear. I'm glad that I've got enough time to explain what I mean by this. I'm not sure exactly what the format typically is of a presentation like this, but I would say that if there are immediate questions as I explain this, then you should feel free to interrupt me as we go. It's always nice to have questions answered immediately, as opposed to saving something until almost the end of the talk, and then having all kinds of confusion that maybe other people shared at the same time. So as I'll show you in a moment, it's very important what Sergey says about the fact that I've moved around a couple of times, because it's been one of the core influencers on this work. I've just spent a little bit of time explaining something about Stellenbosch to a small group here, which was very interesting because with the student exchange, it would be nice to encourage people to come over to Stellenbosch and, of course, to work on this kind of thing with us, which forms maybe not the largest of our ongoing research pushes, but one of the things that is certainly interesting to us and also very promising. So, okay, let me jump right into what I mean by this and also give you a little bit of motivation for the underlying thought process behind this. So many of you probably in this room are also algorithmic specialists of some kind or another. I wouldn't characterize myself as being a general algorithmic specialist, but rather someone oriented towards formalisms for inventing algorithms, formalisms for proving algorithms that correct, and of course taxonomizing the algorithms, which is one of the other key things that I'll get to a little bit later. But one of the observations for me, at least, is if I look at the very famous people having invented many algorithms, we have, of course, tremendously smart people that were with this field from the very beginning. And in a sense, they had an open field for them to explore and invent new algorithms. There were also, even through the last years, people who were able to find interesting new areas to take algorithmic research and new things to come up with. And I would say that many of those people depend on having a significant amount of built-in talent. So it's always very impressive that they've managed to do that. And when I read through these papers in, for example, the Journal of Algorithmics or CACM, of course, as well, it's fair to say that they've got deep insights that led them to designing these algorithms. Every now and then there's also, of course, someone that comes up with something purely by luck, so there's nothing wrong with that as well. But I would like to present today a more systematic or methodical way of looking at a specific field, and I'll show a few examples here. And once you've tackled it in that kind of systematic way, then we can also see the opportunities for new algorithmics and the areas where we can still invent things. And it's fair to say that even with some of the older fields, so stringology or algorithms on strings is, to me, one of the oldest fields in that the first algorithms were already at the beginning of the 1960s. But many people sort of felt that this was an area that was closing off or dying off and became less and less important, or everything had already been explored. But it's certainly not the case. There's certainly more algorithms left there for someone to come up with. Then the other important thing is to say there is also a certain percentage of software, or fraction of software, which I'll get to in just a moment, which is correctness critical in a sense. So this is software that either forms some part of a system which is life critical, so avionics, automotive, healthcare, things along those lines, or it's something that's deep in a software library, so it's fair to say that sorting, searching, many of the container-oriented data structures fall into that category as well. And there we could say that not only is the performance critical, but also the correctness of this is critical as well. And that really is a game changer in terms of how we can come up with new algorithms. So surprisingly, and this comes now back to this area of stringology, surprisingly there are even algorithms which were published by some of the famous people, and then some number of years later were shown to have minor flaws, usually in the corner cases, of course, and this reflects the fact that they had deep intuition but didn't always have the mechanics to be able to carry out the correctness proofs in those corners. So I'd say that's one of the important things there as well. So now what do we do in correctness by construction? So I'll give you a little bit of an overview as to correctness by construction as well. But the idea there is that we always start out with a fairly simple looking algorithmic problem. And you can, of course, also do this for the invention of data structures. You can do this in a couple of other styles as well. And the style that I'll present today is really algorithmic oriented with imperative programs. So in other words, not functional programs or logic programs, but simple imperative programs as the example. And we start out with a pre and post condition. And what we would like to be able to do is, starting with that pre and post condition, use a calculus or a set of techniques, and hopefully not too heavyweight to be usable in practice. We'd be able to arrive at a program in the end, along with all of the annotations which show the correctness of that program. So it's very important to say that we call this a kind of lightweight correctness by construction, because the notion of correctness by construction has been around for many, many years. But lightweight in the sense that we wouldn't like this to be too notationally onerous. And I think by the end of this, many of you will probably realize that this actually could be made more interesting if there are appropriate tools available. So as of the time that we're talking now, there are very few tools available to completely support this correctness by construction, or CBC approach to inventing algorithms. And we'd like a kind of Eclipse plugin or some other sort of development tool that fully supports that, along with each of the refinement steps where we eventually arrive at the algorithm. And when I say support, it could mean support for doing some of the automated proof checking, or for typesetting the algorithm, or just for keeping track of all of the refinement steps as we go, and some of the alternative choices. And it's this notion of alternative choices that becomes somewhat important later on as well. So if you don't do CBC, which I think most of the world doesn't do, unfortunately, so we're some of the few evangelists for doing correctness by construction. If you don't do CBC, how else are you actually developing algorithms? So I think we shouldn't be ashamed to admit that many of us code as well in many of these other alternative ways of doing things, what I call the other camp, if you will. And this means that you simply think in terms of a huge amount of testing. If you're lucky and you've got a fairly limited problem, or you're checking protocols or something along those lines, then there are notions of verification, and that becomes very important for many kinds of avionics, automotive, and other life-critical systems. So verification becomes important as well. And of course, a very popular way of presenting algorithms with a notion of a post hoc proof, which really means that we've come up with this algorithm, and we believe it to be correct because we've had the insights that led us to believe that it's correct. And now we're going to build a correctness proof surrounding that. So it's fair to say that virtually all presentations of new algorithms nowadays sort of follow that style. Fortunately, I mean, there are at least a handful of people in the room who are very familiar with the other way of doing things, so I'm not preaching to the unconverted, shall we say. So a couple of quotes, and these are things that some of these people have said directly to me. But a discussion with Strostrup, and here the notion really is that infrastructure software, so this is software that lies at the base layer of operating systems and compilers and so on, is in a sense somehow more important. And this actually has stronger quality and elegance and of course performance requirements as well. So this would be your container libraries or anything else that is strictly used at that level of software. The other person that said something that relates to this, and now this is maybe a little bit out of context because I've still got to come to the explanation of how taxonomies fit into this, but we've been able to taxonomize fields of algorithms, and it's actually armed with the taxonomy or the classification for the existing algorithms, that we're able to see the holes, which are then opportunities for coming up with new algorithms. And that's what I'll demonstrate in brief a little bit later on. But Tony Hoare, who of course did a lot of algorithmic but also correctness-oriented work originally in this field, he went on to say that taxonomies are to the field of algorithmics what the standard model is to particle physics. So those of you that know about the standard model will probably know that this is our current best classification of particles. And of course we already know that it is to be extended. So we know that these things aren't perfect, but it provides us a structure in which to reason about these things. So back to correctness by construction, CBC. I've given several talks about this kind of thing. Occasionally I talk about taxonomization and not so much about inventing new algorithms. So that's the nice thing about what we're going to discuss today, at least. But the field is very far from being a new field. This quote down here, I'm not going to read the whole quote to you, but the original proponent of correctness by construction would have been Dijkstra. And Dijkstra happened to have been in Eindhoven Around the time that I first arrived in Eindhoven was when he moved to the University of Texas in Austin, but he left behind in Eindhoven a legacy that he, of course, frequently came back to in Eindhoven as well, of doing things in the CBC-oriented way. And this sort of fell into two different camps, people's perception about CBC. The one is sort of the people that really believed in this very formalistic way of deriving algorithms, coming up with an algorithm from an original specification. And of course, then there's a large body of real-life software engineers. And the quote that we see down here from someone who I don't even know, but he made this quote in an Amazon book review of Dijkstra's book. So Dijkstra's book, to put it in context, is something from the mid-1970s. And it's the original book about this kind of field. But this gentleman, who's probably a very good software engineer, does say that this is a little bit like having a book called The Discipline of Calculus and trying to persuade engineers, in particular civil engineers or mechanical engineers, that they should use all of these first principles as a way of actually building real-life bridges or mechanical systems. So James here has actually a very good point. The formalism is something highly appropriate from the 1970s. It didn't grow with time, and it didn't scale up to large-scale software systems. And it sort of fell out of favor with people teaching software engineering, teaching algorithm design. And as a result, fewer and fewer people even know how to proceed in a CBC fashion. And I would say that's maybe not so bad if you're building real-life software. Certainly if you're building things like web applications, it doesn't really matter if it's entirely correct. You always have an opportunity to fix it later on. But there still remains a kind of core of software where it is important to be able to do that. So Dijkstra himself didn't, of course, do all of this on his own. He worked in those years with Tony Hoare on the one side, also people like Floyd, many of the original people in computer science, also here in Russia, were key factors in coming up with the underlying theory that surrounds that. But Dijkstra is the guy that wound up with his name not only on the graph algorithm, but on this way of looking at the design of algorithms. So to continue with the history, there were quite a sequence of books that flowed from that. On the right panel here, you'll see the book that my co-author and I did a couple of years ago. And this is not a sales pitch where I think you should go out and buy our book. Many of the other books are extremely good. And in particular, the book in the middle by Carol Morgan, Programming from Specifications, is an outstanding book that has gone out of print. And Printers Hall gave the copyright back to Carol Morgan, and he has the PDF for the book also on his website. And depending on your digital library subscription, you probably have access to these other books as well in any case. So one of the originals, this is now from the early 1980s, I think was the first edition of Science of Computer Programming, but David Gries attempted to update Dijkstra's original work and make it more accessible, but still it was really something that needed a lot of notational machinery and a lot of deep insight into how to proceed, a lot of familiarity with predicate calculus, and a lot of pattern matching actually over formulae in order to decide how to proceed with designing an algorithm. And what we argue, not only what I'll argue in this talk, but what we argue in our book, and to an extent what Carol Morgan argued as well, is that there are much more lightweight ways of proceeding where you can achieve a more or less similar effect, but without getting stuck in all of the deep details. And this allows, at least in my case, allows us to move a little bit more rapidly through the field and allows us to then come up with the algorithms much more quickly, and there's something somewhat more pleasurable about proceeding in that fashion. So, okay, once again, please do stop me if there are any questions as I happily talk away. So what is CBC? So CBC, as I said, is correctness by construction. But basically it boils down to constructing an algorithm or a program. So we're talking about a relatively modest amount of code that you'll come up with in the end. It comes from a specification, so we of course need a pre and post condition. There are other formalisms in which we could be specifying this. And in particular, if you wanted to proceed to designing parallel algorithms, then there's an entirely different formalism that you proceed with. And we'd like to have some sort of refinement rules or correctness-preserving transformations, which are then the key factors in us arriving at a correct algorithm in the end. But not only that, each one of those refinement steps should be small enough as to be believable. So we don't want to make big leaps that actually leave someone wondering, is this really correct? Or has something been done that's somehow magic, or the wool is being pulled over my eyes, or something like that. So we'd like nice small refinement steps, and we'd like the correctness of each of these refinement steps to be, let's say, more or less self-evident, so that you find it believable, but it also serves a pedagogic value. So in other words, rather than showing students, typically between first and third year students, and we even did some of this in first and second year in Eindhoven, but instead of just showing a student an algorithm and giving a kind of operational reasoning about the algorithm, you'd also be able to present the derivation of that algorithm from first principles, arriving at that final algorithm, in a way where they find each of those steps believable, and of course the composition of all of those steps from the beginning point all the way to the executable algorithm is then in totality the correctness argument for that algorithm, in addition to having this pedagogic value as well. So as I said right at the beginning, we'll do this, at least in the case of this talk, purely in terms of imperative programs. So standard-looking pseudocode algorithms. The programming language that we use is the so-called guarded command language, which interestingly is actually originally on the one side invented by Dijkstra specifically for this, so has a certain elegance to it. But we've discovered in the last few years that there are more and more problems of readability. So when we submit papers to conferences or journals, we find very often that reviewers actually have concrete difficulties with understanding this particular pseudocode. So to me at least, having grown up with this in a sense, it doesn't look weird, but I wouldn't be surprised if you find it looks just unusual enough. So you can view it as a kind of pseudocode. I'll point out where there are significant differences. And then secondly, we need some notion of a logic. So in our case, we're going to have a fairly simple first-order predicate logic. There's some potential holes in this, but they're not relevant at all for this talk, and actually not relevant for inventing new algorithms, simply because we actually know what those holes are, and we're not even attempting to be overly formalistic. We're attempting to really just present this in a way that's believable. And of course, if we even ever need to provide the full proper correctness proof, we know which parts need to be filled in as well. So let's dive in with a short example. The way I'll proceed, by the way, is to show a couple of examples like this. Then we'll take a step back and actually have a look at taxonomies or ways of classifying these algorithms. And I'll show you a couple of parts of a taxonomy. And then I'll give some concrete examples of new algorithms that we've managed to come up with that fill in parts of that taxonomy. So in other words, having looked at the taxonomy, the family tree of the known algorithms, we can identify alternative choices. And I'd like to present it as a way that looks absolutely deterministic and scientific, but there is, to an extent, a certain amount of art involved in all of this, because there are, of course, different possible taxonomy trees that could be presented as well. So hopefully this notation is not completely unfamiliar to everyone, but what we'll come up with over the coming couple of slides is the notion of a sorting algorithm, and we won't refine it all the way to being a proper full-blown sorting algorithm, but just the essential details of one of the algorithms, or one subpart of the family of algorithms. And the notation follows these Hoare triples, and the Hoare triples, for those of you that haven't seen it, are expressed like this. So P, S, and Q are typically the letters chosen, not for any really good reason. But the P appearing here at the front is the precondition. So any of these predicates or assertions, if you will, from programming languages are then expressed within the curly braces. So these are the first order predicate logic. And the postcondition is Q, appearing also, of course, in the curly braces. And then the S in between there is some sort of statement. It's a program statement, compound program statement, that's still to be refined. You can see for the purposes of this this talk, we're not going to talk in detail about the particular data types. I'll do that verbally, but we're not using any notation for that. But what we're expressing here is that if the program starts in a state where P is satisfied, so in other words, assertion P holds or is true, and then statement S executes, it will then terminate. So this is termination oriented. So it will come to a halt, and Q will then be true. And we want, of course, to invent or fill in or elaborate through refinement steps statement S in such a way that it actually is a valid program. So we then are driven entirely by our precondition and our postcondition. So now let's start out with a particular example here. We assume that we've got some sort of array A that we need to sort. So we're treating a sorting algorithm. We don't really care what the contents of the array are. We, of course, assume that it's an array of some sort of homogeneous data type, so an array of integers, but it could be an array of strings or something along those lines. And we put a fairly simple looking, and it turns out this, by the way, is not necessary, but we put a fairly simple looking precondition at the beginning here, and we say that the array is not empty. So in other words, the length of the array is greater than 0. And that could, in principle, allow for a couple of particular refinements in the end, although the one that we'll come up with is immune to that. So that turns out we could have actually just put true in there as our precondition. Then we've got our S here. And once again, that's something that we still don't know. So we're still in the specifications phase. And then our postcondition is that the array A is sorted. And here, this is what I mean by using a kind of lightweight methodology, because we're not really interested in filling in all of the detailed specification of what sortedness means. We could, of course, go and give a universal quantification over each of the elements within the array and actually say that it's less than its neighbor according to some sort of ordering. So that actually would have been the intuitive correct way to go about this. But we leave that for believability, and I think that any reasonable reader would actually find that a reasonable thing to do. So what do we do next? Now we have a couple of possible ways to go about this. But we have an intuition that the postcondition here, the sortedness, means that there's a quantification that appears there, and it really means that each of those elements must be in the correct position, or at least compared to its neighbor, to the right, for example, it must be in the correct position. So given there's a quantification in the postcondition, and we have no a priori upper bound on the size of the array, so we don't know up front what it is, we can already say that we intuitively know that there'll be some kind of loop that we need to have there. And our loop in this case, I can already give you a hint about the next slide, but the loop means that we're going to proceed from left to right, and we could equally well have done an algorithm that proceeds from right to left, but intuitively we're going to come up with something that looks a little bit like this, and we're going to proceed from left to right, and at each point we're going to have an index, in this case I, which points to the current position within the array, and we know that everything, or we're going to say that we know that everything strictly to the left of I is already sorted, and everything from I to the end of the array is unsorted. Okay, so unsorted doesn't necessarily mean that it's jumbled. It actually means that we simply don't know something about the orderedness of it, whereas we actually do know that this is sorted. And hopefully this is readable also from the back of the room, but the notation here means that with the square bracket here, with the 0, means that we're inclusive on the left, so from the very beginning of the array, until, and then the round bracket there means exclusive on the right, means that we're not including position I. So this is the reason that I is drawn a little bit to the right of this boundary there. So up to but not including position I, things are sorted, and from I onwards to the end it's unsorted. So right away you can see, okay, we have some sort of notion of the loop that we're going to use to move from left to right through the array. But we can also say a couple of other important things here, and I think it's fair to say that Dijkstra didn't make a big enough deal about this, and David agrees as well, but the underlying thought process that should drive the design of most kinds of algorithms, and also, quite frankly, most kinds of data structures as well, is the notion of some sort of invariant thinking. So the design of the invariant, and of course the variant related to the loop as well, are then the crucial factors. And we notice from student projects and from the pedagogic angle to this, that providing this kind of way of thinking to students is very important for them actually getting on top of the corner cases. And we see that with algorithms like binary search, of course, where it's very easy for students to get one of the corner cases wrong. So in our case, what would the invariant be? Well, the invariant would be, as we proceed from left to right, well, everything strictly to the left is sorted, and we don't really say anything about everything to the right. Okay, so that's one part of the invariant. Another thing in the invariant that we really should probably say is that I is less than or equal to a.len, so in other words, the length of A. And I say less than or equal to because we'd like to be able to let I run all the way to the end and just off the end, as we typically do in Java and C programming languages. So just off the end, and that's the point at which we'd like to stop. And then we know that everything strictly to the left of it, in other words, the entire array, has been successfully sorted. So we already have a gut feel for what the termination condition would be in this loop. And beyond that, we wouldn't like A to be able to progress any further to the right. So we already have a kind of self-protection in terms of buffer overruns and the kinds of things that creep into real-life software as well. Okay, so what else could we say about this loop? Well, one of the other things that we should come up with is the notion of a variant. So if you were listening super carefully earlier, I did mention that we would like to be able to talk about termination conditions as well. And being able to show the termination of this means that, well, there are a couple of different ways to do it, but one of the easiest ways is to have the notion of a variant. And the variant allows for two things. The variant is some sort of monotonically decreasing integer function that allows us to show progress in each iteration of the loop and also is bounded below. So it also allows for termination, and it allows us to then show those two things which are very important for termination. So you can already guess that there's a class of algorithmic design, in particular algorithms that never terminate, so of course many things in operating systems where this is inappropriate, but piecewise, many of the things that happen inside an operating system, dealing with the process table, many of the other tables, the file system, for example, as well, are all things in which we really would like to reason in terms of termination, and it's only the operating system as a whole in which we don't necessarily care about termination. And so it means this still has a place in the guts or in that infrastructure software side of things, as Strausstrup put it. So what's an appropriate variant in our case? Well, the variant that I've chosen here is the distance from I to the end of the array. So this is actually intended, this horizontal line here with the arrowheads at both ends, is intended to say that the distance that we've got to go until the end is our variant quantity. And we can express this directly. That's a.len minus I. And we know then that this won't decrease below 0. So anytime it's decreased below 0 means that we've gone and proceeded with I even beyond the element at the end of the array, the sentinel point at the end of the array. So we have a direct termination condition there. And of course, we can clearly see that this quantity would decrease with each iteration through the loop as we make progress from left to right. So that seems fairly straightforward. Now, if we had to then go and express this in first-order predicate logic, that's also fairly straightforward. It starts looking a little bit ugly, and this is actually exactly where we get to the conflict between this kind of diagram and the one before it. And of course, what you still see here at the top here is the diagrammatic view of this. And alternatively, in the bottom half of this slide, you can actually see what this looks like if Dijkstra were to express this himself. So the invariant in particular is that we know that everything up to but not including I, so I leftwards, is sorted, so that's been expressed here. And then, as I said earlier, the other conjunct that we already know we'd like to express is that I hasn't run beyond the element at the end of the array. So I is less than or equal to a.len. It allows us to run to that sentinel position but no further. So what could we do with this invariant? Well, one of the things that we should be able to show ourselves immediately is with this invariant, our intuition, once we've gone for I from there all the way to the element past the end here, that should be our termination condition. And we can see intuitively then we've got the entire array having been sorted. But can we actually show that in terms of predicate calculus? And it turns out we can. If we take I, which is our invariant as expressed here, so we take I here, and we do the substitution I is equal to a.len, so you may use a different notation for substitution in predicate calculus. Many of you might use the backslash operator, but we use this assignment operator. So we do a substitution in this predicate of a.len for each occurrence of I, and we plug that directly in there. We wind up with the equivalence to this expression, and this basically says that we know that we have managed to sort that segment of the array from 0 to a.len, not inclusive. And of course, there's every reason to not be inclusive at the end there, because that's actually one past the end of the array. So we know that that's something that's been achieved. And then, of course, a.len is less than or equal to a.len, so that's a simple substitution in there for that I. And we know, of course, that this conjunct is then trivially true, so we can eliminate that entire conjunct. And we know that this is the entirety of array A. So that implies, after we drop that conjunct, that implies sorted of A. In fact, it turns out that's equivalent, but sortedness of A is something that we've then implied. So in other words, once we've got I equal to a.len, assuming we've satisfied that invariant all the way along, we actually know that we've then satisfied the post condition of the entire algorithm. So that's exactly what we'd like to be able to do, and that allows us to make our first real refinement step. So along the way, I've probably told you a lot of boring details about how we'd refine this algorithm. So for everyone in the room who's a computer scientist, this is a kind of trivial refinement, but it typically is something that takes a moment for early students to actually wrap their heads around. And the other thing is, we kind of know that we would need a couple of parts to our algorithm. We'll need something which sets up the invariant. In other words, then the invariant holds after the execution of that. And then we'll need that loop in which we actually do this traversal from left to right. And as we do the loop, the traversal from left to right, we're going to have to do some fiddling within the array to make it sorted. And then we've got the complete algorithm. So S2 here is where we're going to put the loop. S1 is something that needs to establish the invariant. So that's why the invariant has now appeared here as one of our assertions in between. And of course, the precondition and the postcondition are as before from the previous slides. So now how do we establish the invariant? Well, I think you all have an intuition from looking at the previous slide that all the way at the beginning here, if we set I initially to 0, then trivially everything strictly to the left of I is sorted because there is nothing to the left of I. So at the initial condition with I equal to 0, the invariant actually happens to be true. And we can see that formally by doing again the substitution with an initial value of 0 for I. If we plug that in there, then the sortedness of this segment of A, which consists of an empty segment, that's trivially true. So every element in the empty segment is, of course, sorted or in its correct position. And, of course, 0 less than or equal to A.len. So this is also a direct substitution into the invariant, where 0 was substituted for the occurrence of I there. And now we also know that, well, we already said that A.len is actually greater than 0. That was our precondition here. So that's certainly true. And these two conjuncts together are true. So we can do that immediate substitution. S1 should actually be this statement, I equals 0 to start with. So let's have a look what the collective algorithm looks like. So now I've made a bigger step here. And I can assure you that I've only done this sort of larger step in the interest of time, that we can actually cover some of the other material. But the bigger step here is to actually fill in the details of the algorithm and also fill in some of the intermediate details of the particular derivation. But the first part up here, we can see this is the precondition. This is our initialization of I. We've got a bit of a notation here. We typically actually explicitly state what the invariant is and what the variant is. And then here at the bottom of the do loop, we have finally our post condition, and I'll come back to that in just a moment. But we also know that we have as our loop condition the fact that we haven't yet reached the final point. In other words, we haven't reached the point where I is equal to the length of the array. In other words, we've run off the end to the sentinel element. And there we can say we're going to continue executing this loop as long as it's not true that I is equal to A.len. So of course, this is trivially rewritten to be I is not equal to A.len. Many of you coding would probably have written something like I is less than or equal to A.len. And there's nothing wrong with that, but if you actually go with less than or equal to, then you have a slightly more difficult time actually proving the correctness in the previous slides that I've shown you. So once we've got this, inside the body of the loop is where we still have a little bit of work to do. But one of the things that we can always guarantee inside the body of the loop is at the very top of the body of the loop, the invariant is true. Okay, that's why it's called the invariant. The other thing that we absolutely know is true at that point is that the guard of the loop is true. So if the guard weren't true, then we wouldn't have arrived at that point either. But that means we can have an assertion here which says that I is true, and furthermore, I is not equal to A.len. So those are two things that we can actually use to refine the statement S3, which will then be something that actually does some sorting related stuff within the body of this loop. Then after we've done some sorting related stuff, we also want to move I onto the next position. And we can do that with a simple I becomes I plus 1. And there we can actually do a bit of proving related to the fact that the variant has then decreased. So in other words, A.len minus I, that's our distance from I to the end of the array, that has decreased. And we can clearly see that it has decreased because we've incremented I over here as well. We can also see that it's non-negative because, well, we started out with I not equal to A.len, and we know that it was strictly less in that case. then we know that even after we've incremented this, our variant has not gone below 0. And we must design S3 in such a way that the invariant is true at the bottom of the loop as well. So that's crucially important. At the bottom of the loop, we know that we have now moved I one step to the right, but that invariant must still hold. That means the sortedness of everything strictly to the left of I must still hold, and we need to design S3 in particular with that in mind. So the final thing that I'd like to say about this before I discuss S3, and I'm just going to do that verbally, but the final thing that I'd like to say down here at the bottom is, of course, the only time you exit the loop is when the guard is not true. Okay, so we may have skipped over the loop entirely if this was an empty array, but in any case, the guard is not true, so this is a double negation here, which turns out to be I is equal to a.len, which means we've actually run to the right end of the array. And of course, we also know that the invariant holds, and these two things together, well, we've already shown that those two things are equivalent to sorted, and that means we've then achieved our post condition. So now, just to talk you through what we could actually do with S3, here we would actually probably bore the audience by going through all of the details of S3, but all we need to do is, before we move I one position to the right, we need to do something with the element of A that sits directly there. We know that everything strictly to the left of I is already sorted, so we need to do something with that element at the position I, and there are a few choices there. We could actually do, for example, a binary search within that portion of the array. We could then make a kind of insertion sort algorithm, so that would be one clever way of doing it. One alternative would be to say, well, we're not going to do a binary search, that's too complicated, or we don't know about that, but we're going to continually exchange elements until that particular element has bubbled to the correct position within that sorted portion of the array. And in that case, we've moved everything up in the array as need be, and we've bubbled it down to the correct position, and then everything's back in sortedness as well. And then we'd wind up with an algorithm that we call bubble sort. So right there with two fairly simple choices of how to come up with the body of S3, we can have insertion sort or bubble sort, which are two, of course, of the very well-known algorithms, which have all of their own particular performance characteristics as well. So both of those follow directly from taking this specification, and in isolation, you can then give that specification to someone else, in our case, hopefully to a clever student, and have them work out the details of that and then come up with an algorithm, get another student to work on another variation of that, and have a completely different algorithm. So in a sense, we've come up with a family of algorithms here, which is a very important observation because we've got a kind of branching here within the algorithm derivation that allows us to go in a few different directions. Excuse me. So that's, I think, a fairly straightforward way. Any questions so far now that I've gotten to the end of sorting algorithms? So we don't have an enormous amount of time left, and luckily I'm not going to treat everything in this level of detail. So there's a certain element of acceleration in the rest of the discussion, but hopefully I've given you some detail about the use of CBC to arrive at this level of detail within the algorithmic specification and the refinement of the algorithms. So over the next couple of slides, I'm just going to show you another fairly simple looking problem, which then has an interesting looking family of algorithms. So this is really a trivial problem. We've got some finite set n, so these are nodes, that's why it's called n. And we've got a function from n to n, so this is a total function. So every node is mapped to some other node at least, and of course you can see node 0 there is a kind of singleton node. Everything else is mapped to another node, and there's of course a cycle appearing somewhere there in this carefully designed example. And we'd like to know the F closure of a particular node, so we'd like to be able to compute in this example the F closure of 4, and we can trivially see here that that's 4 as the reflexive closure of 4, and then of course the transitive closure leads us to 6, 7, 8, and then also to 5. So you can all imagine that this is a fairly simple, I would even argue this is probably the simplest possible graph algorithm that isn't completely trivial to specify. And the details of exactly what I mean by closure is then given here, but I think this is something that everyone envisions very quickly as well. The slides, by the way, you're welcome to have afterwards and look at them in some detail. So now how do we specify this? Well, we essentially get to say the same kind of thing within the precondition there. So our precondition says that n is a finite set, and of course we've got our complete function mapping nodes to nodes. And we also have our initial node here, and this is something then given to us. You could say that this is actually the argument or the input parameter. So I didn't discuss that under the sortedness, but also if we were to specify the sorting algorithm as a procedure, we would then have array A as being one of our input parameters. So here we simply specified in the precondition, and in our postcondition, we would like to have collected in some set D the F closure of our node that we were given at the very beginning. And D here, there's a bit of a specific choice in the names that I've used here. D is for done, and excuse me. D is for done. We already on the previous algorithm went and used I for the invariant. So here I've gone and used J for the invariant. But we would like to, in a sense, be able to start with two sets, one called done and one called to do. And the done set would be the set of nodes that we've already visited. And so at the end, it should actually consist of the F closure from N0 or N0. And as we actually proceed through the algorithm, we'd like to be able to do this layer-wise. So given the number of steps that we've done so far, the done part consists of all of the F to the Ks except for the ith one. So all of them up to but not including the ith one. And then the to-do set, which is why it's called T, should consist of the set of nodes to be done. And of course, you can probably already see that this is, of course, a singleton set. But if we had a more interesting way of manipulating graphs that are more general than this, we would then have this be a non-singleton set, and that would actually then either be a stack or a queue, and that would dictate for us whether we have a kind of breadth first or depth first traversal of the graph. So these are very important data structure choices that we arrive at in the end, but we start out in the beginning with specifying it as being something generic like a set, and that allows us a lot of leeway to then make those specific choices a bit later on when we refine into a particular algorithm. So now we can jump, unlike in the case with the sorting, we can actually jump ahead a couple of steps. And here I've simply copied the precondition that appears as is at the top here. The postcondition appears as is at the bottom here. And we know that we'd like to proceed stepwise through this. We simply need to initialize the done and the to-do sets. The done set is, of course, the empty set to start with. The to-do set is our N0 because that's the F to the 0 of N0 is the reflexive under F itself. And then we've done 0 steps so far, so that's why the 0 appears there. And then we have the invariant. And we simply proceed through each of these steps, and we'd like something filled in the body here. This is going to be in our S0 statement here. And we proceed as long as T is not equal to the empty set. And we know that at the beginning of the body of that loop that we, of course, have this guard of the loop is one of the things that holds. Also, the invariant is something that must hold. Then at the bottom of the body of the loop, we also know that the invariant must hold again. Very important. So always J will then hold there. And we know then after the loop, J will hold. And of course, the negation of the guard will hold there. So in other words, if the guard is T not equal to the empty set, then finally we know that T is equal to the empty set. And we jump to there. And we can, of course, rationalize that J and T equal to the empty set means that we finally arrived at the end and we've computed this. So we have a little bit of a problem here with expressing an appropriate variant, which is actually one of the reasons we came up with this example. And the problem here is we'd like to be able to say something like, well, we've got a notion of where we're going to get to in the end, and the size of that set minus the size of what's been done so far is actually the distance that we've got to go. So this would be our variant, and that's a reasonable thing to express. But of course here, writing this down in the invariant means that we're expressing something which actually depends on the to-be computed result. So this is perfectly okay for us to write down here at the bottom right in terms of us reasoning about it, but expressing this directly then as an assertion, if we're coding this, that's of course a no-no, because this expresses something that is part of the ultimate aim of the algorithm. So we could come up with a much looser variant, and that is that we know that n is, of course, a finite set. So the variant could be the size of the total finite set minus the size of what's been done so far. And that seems like sort of the best compromise that we could come up with, unless we had some more reasoning about the structure of the graph. So okay, let's skip to the final version of this algorithm. Here I'm absolutely not going to talk you through the detail of this, because this simply gets into too much detail compared to what we want to accomplish today. So if there are no questions, if there are questions, obviously bring them up as we go. But I'd like to then move on to what we can actually do with these kinds of derivations. And as I said earlier, there are a couple of people in the room that have seen this in large amounts of detail, so I apologize to them for seeing this again. But one of the important things is that once we have an algorithm derivation, so starting in the case of the sorted algorithm, starting with this completely generic abstract solution, and working our way down to a specific algorithm that's implementable, so in the case of bubble sort, or taking a different branch in the case of insertion sort, or perhaps a completely different path, and coming up with quick sort, all of those different derivations, piecewise, can actually be put together and prefix factored into a tree. And the tree starts to look interesting not only in terms of actually sharing material through the derivation, but if you take a look at the example of sharing in other fields, and biological taxonomies are, of course, where a lot of this originated, where we can then use this classification, and in fact, there are many other ways that this could be classified as some of the people in here have worked on in particular. But in this case, we're going to view this purely as a tree. And armed with this, of course, we know that we can take two arbitrary nodes here, and we can look at their nearest common ancestor, and that says something about their variances. So this is a very important factor in software engineering and variance engineering. And we can also look at their commonalities, and their commonalities are the part from the root all the way down to the splitting point here, and that can form a body of shared code as well. So there's a very non-trivial software engineering component to this as well. So in the case of algorithmics, we can actually make similar steps, and classification of the algorithms is then done purely on the basis of these derivations. And once it's presented as a taxonomy of the algorithms, it's got a certain pedagogic value. You could actually view this in a sense as the table of contents for that family of algorithms, so a way of reading that family of algorithms. And to be honest, most students are never really going to care about a breadth of different sorting algorithms, unless they're in particular in search of covering all of them, understanding all of them, or potentially inventing some new algorithms. So it has some specific usages as well. There's a potential that it can be expressed as a DAG, as a directed acyclic graph. And the reason there is, of course, you may have different paths that lead to the expression of exactly the same algorithm. And that becomes interesting as well. I mean, this is something that could be glossed over, but two different derivation paths reflect that they can be arrived at in two equally legitimate ways. And I say that because there's a certain matter of taste in expressing this kind of taxonomy tree. You can have taxonomy trees that are purely based on the granularity of the algorithm derivation that you did, and if you'd made some other choices or done things in a slightly different order, you would have come up with this in a completely different way as well. So this is a very important factor in the aesthetics of this, shall we say. So, what do we have in this? Well, now this is actually, I think, the taxonomy graph or something very similar to the one that Sergey used in the online poster for this talk. But this is a taxonomy tree for keyword pattern matching algorithms, and this is an area of stringology, as I mentioned before. It's specifically chosen because I think many people in the room will be very familiar with them. And at the root here, we have the absolute most general specification of an algorithm, and I'll come superficially to that in just a moment. And whatever you write at the very top here is something that's absolutely unexecutable. It's simply the precondition, the postcondition, and a magical body of that program, which is still to be filled in. So the root is unexecutable, unless you had an absolutely magical programming language. But then every step that you make from the root downwards is potentially something that's reaching executability. And that could depend, of course, on the programming languages. We've actually noticed before that, if you write things very often in a set theoretic framework, you might find a domain-specific language like SETL, or one of the other higher level languages like that, is something that could actually be used for coding up one of the algorithms that appears closest to the root. So I think the usefulness of the classification is something that we'll revisit in just a moment as well. But just to reiterate, the commonalities and the variance points are the two most important things that we reflect on for the possibility here. Okay, now the secondary goal, and I find this actually sort of the most exciting part, certainly in the last few years, because if we look at no, sorry, it's not in this slide, but if we look at some of the underlying work, and there's a set of references at the end, partial set of references at the end, some of these taxonomies that we've been working on are things that already date back 25 years. So we've had to keep updating the taxonomy graph as algorithms are invented in completely other formalisms or using other ways of inventing algorithms. And as we've done that, we've actually been able to keep on top of where there are potential holes in the taxonomy graph. And the potential holes in the taxonomy graph are often very easy to see visually, even without knowing a lot about the taxonomy. But you could see down here there's potentially some sort of thing that's been missing, or a cluster of algorithms there that's been missing. And once you actually know the taxonomy intimately, it turns out to be even more easy to see the alternative choices that could have been made. And this brings me back to one of the points that I made right at the very beginning of this talk, and that is if we had appropriate tool support, this is something that could be automated fantastically. We could be able to then generate some of the code directly out of a taxonomization effort, but we would also be able to generate the LaTeX to be able to present a taxonomy, or of course all of the proof obligations, which could be then fed to a theorem prover and automated as well. And so there are quite a number of people working directly on this, another potential area for collaboration in the case that anyone's inclined in that direction. So other people working on this are, of course, a little bit fragmented depending on the fields that they come from. So what can we apply this to? Well, it turns out there are a few areas that we've already applied this to, and there's a specific reason that all of these fields look very, very old. So in particular, anything related to regular grammars, regular expressions, finite automata, string pattern matching problems, as I mentioned earlier. And the reason that these things tend to come up in the case of designing our particular taxonomies is because these fields are reasonably complete. The same thing goes for sorting algorithms, many kinds of data structures as well. If it's an absolutely new field, and I would actually characterize many of the FCA algorithms a few years ago as being exactly in that category. If this is a very new field, you don't always have enough algorithms to be able to create a taxonomy, but you can of course already create a skeletal taxonomy that can guide the individual choices towards inventing some of the new algorithms as well. So our choices have tended towards being some of these much older algorithms dating back all the way to the 1950s and 1960s, if we look in particular at stringological ones and finite automata and regular expression related algorithms as well. So you could say these fields are absolutely dead fields. I mean, they've been overexplored, they've been explored for decades. In fact, some of them since before anyone in this room was born. So these are fantastically old fields. And it's a pleasure working in them, but one of the problems is that they actually use so many different notations that you actually need to then go and tease out of each of those old algorithms a kind of restructuring and rederivation in a CBC style in order to taxonomize it. So behind all of this taxonomy-oriented stuff is, of course, a not so trivial amount of work, and that's actually why we have master's and PhD students working on this kind of thing and being able to distill out of this what some of the underlying details are. So back to one of the examples here, and I suspect we're not going to have enough time for me to discuss this in huge detail, so I'm going to sketch a couple of the individual choices, and then I'm just going to show you some examples of some specific algorithmic advances that we've been able to make specifically in this field. And this is keyword pattern matching, so just to give you a couple of connection points to what you probably already know in terms of keyword pattern matching. There's some of the original algorithms, a very naive algorithm. There's an algorithm by Knuth, Morris, and Pratt. And in fact, preceding that, there was an algorithm by Morris and Pratt before Donald Knuth joined that effort. There's a whole family of algorithms known as the Boreum-Moore algorithms and Boreum-Moore horse pool. And then, of course, many algorithms that follow on from that. So one of the first taxonomies that we did, and it wasn't the first classification, because there was one before that, but one of the first taxonomies that we did is already now 25 years old. But as I said, we've had to continually update this, and our most recent update, unfortunately, is already 7 years old. But things significantly slowed down in this field to the point where, without using techniques like CBC or inventive algorithmics, it was remarkably difficult to come up with something new. So let me give you a quick tour of some of these algorithms here while I still have time. I'm just going to sketch the algorithms, and then, as I say, I'll show you what some of the refinement steps look like without going into the details that we discussed with the sorting algorithms. So the first possibility that we could have, and there's a string that we're pattern matching there, The keyword pattern matching problem is we have some sort of input string. This is typically a finite input string, so there's a dot, 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 ellipses on both sides there, but it's not intended to say that this is infinite, but this is just a part of it that's visible at this time, and we'd like to know where each occurrence of a particular keyword is, so that's the pattern that we're looking for, and this is the pattern occurrence or keyword pattern matching problem, and this could also be overlapping occurrences, so that's fairly straightforward. Now in this case, it's not really easy to have overlapping occurrences because what we're looking for is the keyword baby, and you can see that if we started here, we could attempt to make a match there against baby, and we could use something that's structured like a finite automaton here, very simple looking sausage-shaped finite automaton, and we could make transitions in there. We have a failed transition here because it starts with an A, we have another failed transition, another failed transition. We finally get to this point here, and we make a successful transition, but then we get stuck at the next B here, which is not possible, but we can actually then move one step to the right, and we can make a successful transition there, but then we get stuck with the D. And we proceed that way until we finally get to this point here where we consume this B here, the second last B in the window at the top, and we consume that one, and then we actually consume the next 3 characters after that, and we've got a successful match. So okay, that's a naive algorithm because at each potential step we've moved only one step to the right. We've restarted our matching attempts and done that from scratch. Now, how could we do this a little bit smarter? Well, there's the notion of prefix-based pattern matching, and this is actually something very similar. This is essentially the underlying idea with the Knuth-Morris-Pratt type algorithms. And here we have a much more elaborate-looking finite automaton. The beauty of the work originally by Knuth, Morris, and Pratt back in the 1970s, so you can see already the age of this algorithm, but the beauty of the original work was to figure out a way to make this highly compact. So it's a rather complex-looking graph, and it turns out in automata terms that it's impossible to compact this unless you're willing to sacrifice a little bit of running time and then work with 2 different data structures. So that's a brilliant way of doing it, and I'm not going to walk you through it here, but here we can essentially always make a forward transition, make a transition, so we never have a possibility of getting stuck, but some of those transitions might take us back to a previous state. So for example, when we're here and we see these 2 B's in a row, we consume one B and we get here, we consume another B and we stay in the same state, and then of course we see the D, which takes us back then to the start state. So we always make a transition, we never have to revisit the same character twice, and this turns out to be a fantastically efficient algorithm in practice. And in fact, a generalized version of this for multiple keywords, a finite set of keywords, is exactly what underlies a lot of the network, hardware-implemented network algorithms for things like routing, but also security algorithmics. So a very important algorithm in that sense. Another possibility is a family of algorithms that you may have seen before called the Boreum family of algorithms. These are rather interesting in the sense that they attempt to make a backward match. And so here we've got a finite automaton which actually represents the backward version of the keyword. And we start here and we look backwards. So in other words, from right to left, we try and consume the B, which is not possible. And then we move to the right. We try and consume the B again. That's also not possible. We move to the right. And you can see eventually we arrive at a little bit of trickery where at a certain point we've got the letter D here, which was consumed, and that allows for us to make a further shift to the right than just the one element to the right. And this is the beauty of these so-called Boreum family of algorithms, because these greater shifts are based on the fact that this D here has no possible way of appearing anywhere in the keyword baby. So we actually know that we can shift the entire window 4 characters to the right and then make some progress. So brilliant algorithm, and this was only barely improved by something known as the factor-based algorithms, and that's what this looks like. The factor-based algorithm is actually another kind of automaton, another kind of tree-based automaton, which is really just structured around all of the factors of baby, and it allows us to make some more rapid shifts to the right by picking up a little bit more information on each attempt and then using that information to make 2 shifts to the right, and eventually we arrive at the correct answer as well. So okay, what have I shown you? Well, I've shown you actually a very operational view of 4 different algorithms here. I can tell you already that I've taken you through a little part of the taxonomy tree here. I've taken you more or less from the root, but we actually kind of got down to a couple of these here. Down this way would have been actually the algorithm surrounding Knuth-Morris-Pratt. and the other algorithms proceeding from here, which is the naive algorithm, the very first one that I showed you, is then the root of an entire branch, which leads us to these Boreum families of algorithms. So again, apologies for the time, and also the readability of the amount of detail here. So I don't expect you to absorb all of this detail, but what I want to do is just walk you from some of the root algorithms. I'm going to take you then from this root up here, down through a couple of these, and just show you roughly what the guarded commands look like and what each of these refinement steps look like. And hopefully you find, excuse me, that these are believable with each step of the way. So the first thing that we do is that we write down our post condition, and our post condition is that in some variable O, which was actually named just to be the output variable, so we don't have the notion of a print statement, but we have an output variable, and the job of the output variable is simply to collect all of these occurrences. And how do we collect an occurrence? Well, every time that we found baby in the input string, the occurrence is the left context, followed by the keyword baby, followed by the right context. And you could say, well, Bruce, that's a completely crazy way of doing it. You should actually just be using an index within the string. And of course, in reality, once we get down to actual implementations, we would simply be using indices. But at this point in the algorithm, we can reason in terms of strings and substrings and suffixes. Also because it allows us to then use all of the machinery of formal languages for reasoning about these, as opposed to already getting into a specific implementation detail or representation detail like indices. So we avoid that at the very beginning, and we say, well, we have a program here at the very beginning. We simply assign the correct answer to O, and that means that our post condition is that O must contain the union over all of the possible ways of chopping up the input string into a left context, a keyword, and a right context, all of the possible ways of chopping it up, such that the V is, so the middle part between the context, is our keyword. So this is a fairly straightforward way of expressing our post condition, and we write a program simply to express that. And now we know that this is something that's unexecutable, unless of course you're using a language like Settle. You may be able to express this in Wolfram or Maple or APL or one of those languages, but certainly not in a very efficient way. So you need a lot of quantification machinery. And here this hides the fact that there are actually 3 nested union quantifications, because I've introduced these 3 variables here all at the same time. So we can do a little bit of rewriting. That's our root algorithm, and we always name the algorithms in terms of its root path. So the root algorithm has the empty root path, and our first real algorithm would be that we have a for loop, and this for loop allows us to just consider a breakdown of the string into a prefix and a suffix. And we simply want to take all of the chunks of that prefix, all of the suffixes actually of that prefix that happen to be keywords, and we want to register them. So we've got a simple single loop here, again something that's absolutely unimplementable. And if I go back one slide, it means that we've only gotten to this point within the taxonomy graph, but it's part of the machinery for heading towards one of the implementable algorithms. And we know that this inner loop here, because it also consists of a quantification, we probably also need a loop. So we already know that from the naive algorithm, that we had 2 nested loops, and we drive a little bit in that direction, and we wind up with these 2 for loops. And this allows us to say that, well, we're iterating over all of the breakdowns from a chunk of the string and its right context, and then we iterate over all of the suffixes of that chunk and its left context, and we register any particular matches, and that's what this registration happens to be here. This is a kind of if statement in the inner loop. So that's all fine and good. There are a whole bunch of complicated choices that I'm not going to talk you through here, but it allows us to actually refine this non-deterministic for loop into a do loop, and the do loop allows us to then proceed from left to right through the string or from right to left. So this is a very important step of introducing determinism towards being able to implement this. You could, of course, still write it as a for loop and leave it up to the compiler to then make a choice over iteration over a data structure. But we already know that efficient algorithms are typically arrived at by filling in that kind of determinism all on our own. So what do we have at the end of this? And this is, I think, the only one that I'm going to show you. But at the end of this, we have exactly the algorithm that allows us to express this way of doing the naive algorithm. So we would then have similar machinery for coming up with all of the other kinds of algorithms, the Boreum algorithm in particular. And let me skip over that. And I'd encourage anyone who's potentially a masochist for this notation to read through all of the details. Still very interesting if you're actually interested in exactly why we thought that there's something else to be done in the remaining algorithms. Now, if I stop here at this moment, with the remaining time, I just want to talk you through some of the other possible ways which are not expressed in this taxonomy tree. And the one possible way is that we've already seen how we proceed with the Boreum style algorithms, so all of the ones that exist down in this subtree. We see how we proceed from left to right, and we make skips every time that we can, so larger shifts through the text. And if we have a look at a particular example, here's an example of looking for the keyword abracadabra through the fairly standard text, the quick brown fox. And we start our match attempt at the beginning here. So abracadabra is aligned here. And we make a match attempt, and it doesn't work very well because we already start matching the A with the B here. That doesn't work, so we make a shift to the right. And you can see here I already made a little bit of an efficiency improvement by striking out the characters here at the end. And the ones that I struck out at the end are the ones where there cannot be a possible match because abracadabra simply doesn't fit in that chunk of the input string. So abracadabra here, the B only appears there, so we can shift a little bit to the right, 2 characters to the right, and then we can make another match attempt. And here we get lucky. We try and match the O of brown against abracadabra, and we realize, ooh, okay, there isn't even an O appearing within abracadabra, and now we can shift a lot of characters to the right. So this allows for these larger shift distances within the Boreum style of algorithm. So you can see by the time we get to the end, we've actually skipped over large chunks of the input string. To an extent, we got a little bit lucky because of the semi-disjointness of the alphabets of abracadabra and the quick brown fox. But still, you get the right general idea. And these were, until very recently, some of the absolute best known algorithms and also the easiest to implement algorithms. But you have to ask yourself something interesting, and that is, why do we even go from left to right? What about the possibility of actually starting in the middle and making a match attempt and then moving to the left and moving to the right simultaneously? So this actually was one of the insights from looking at the taxonomy tree, is that we have a kind of symmetry in the problem which has been done away with by people's general left to right obsession with processing strings or processing arrays. And if we recast this as a kind of algorithm, and we've called this the dead zone keyword pattern matching algorithm, here we can do something where we actually bring this symmetry back to life again, and we attempt to do abracadabra within the middle of this input string. And I say middle because we've aligned the left end of abracadabra with the middle of the remaining possible points where we could have a match. And we do that, and we realize, oh, there's actually no possible match. And furthermore, we take a look at what we've learned about the input string, and we use that to say, well, there's a chunk that we can skip to the left and a chunk that we can skip to the right, and we can strike out those portions. And it turns out to be this entire struck out portion here. And that leaves us a little chunk of the input string over here and a further little chunk over here. And we make one more match attempt to the left, and that strikes out everything, and one more match attempt to the right, and that strikes out everything as well. So you can see, as compared to here, we had a significant number of different match attempts. Here with very much the same kind of computational effort, but a different way of looking at the problem. We've come up with an entirely new algorithm because of a hole in the taxonomy tree that allows for this symmetry where we've got simultaneous left shifting and right shifting. So that would be the guts of the algorithm. Whoops, this is unusual. Okay, that shouldn't have been rotated. This is a little bit of a Windows versus Macintosh issue. But regardless, that's a diagram. I'll fix it for the final versions of the slides. And the underlying algorithm is no more difficult than the underlying versions of the Boreum type algorithms that you would read in a first-year textbook. But it's much more elegant. It has its own place within the taxonomy tree. And as I said, it's something that no one else had arrived at in the years following that. So the original Boreum algorithms were invented in the time window from roughly 1975 to 1978. And from then onwards, there was a lot of fine-tuning of those algorithms, which is very impressive actually, the implementations of these algorithms, but no radically new way of looking at the problem as we've arrived at with the dead zone. So the difference between the traditional algorithm and the dead zone algorithm, here I've presented it as a recursive function. So again, this is something I haven't necessarily discussed in any detail today, but CBC does apply to the derivation of recursive algorithms. And a recursive version of the Boreum algorithm differs only from the dead zone in a few tiny places. And we can see here where those places are. So this hasn't made things much more complicated. And it's surprising that no one came up with this separately from us in the intervening years. Here's the best case scenario for dead zone pattern matching. You can see that it takes, on a fairly large string when there's a completely disjoint alphabet, it takes one match attempt there, which strikes out a large section of it. And then we could, of course, proceed to the left here, sorry, this piece here, and we could proceed to the right in parallel. So there's a whole new opportunity for parallelism, which is looking reasonably promising, depending on the kind of hardware. But we proceed to the left here, and we proceed to the right here, and that's completely finished the match attempts for the entire string. So that's a rather surprising result. We've then proceeded with further derivations of that in a more efficient way, so refined it into algorithms that don't necessarily jump around in different parts of the string. So those of you that are implementation people or know about hardware and compilers and so on, probably already know that if you go and look at something in the middle of the string, then you go to the left, then you go to the right. This is not what's known as cache-friendly, so we're already aware of that, and there are ways of doing a similar kind of dead zone algorithm with larger skips through the text, and the way that looks is something similar to this. So the top portion of this, these first four lines, are match attempts by one of the variants of the Boreum type algorithms, and you can see here I've designed this particular case, this particular input to give the best case performance in the Boreum algorithm. So there's a shift immediately, all of these characters to the right, another shift, all of these characters to the right, and so on. And in the case of this other variant of the dead zone algorithm, we've got considerably more potential shifts to the right. So the details of that I leave up to you if you develop an interest in that. And I think for the remaining 1 or 2 minutes, I'm literally going to skip through to the conclusion slides, and hopefully there's some additional discussion or discussion points that people would like to have. And the remaining between now and the conclusion slides is just to show you that we have worked on something very similar for multiple keyword pattern matching. So we're able to match a finite set of keywords without actually doing each keyword one by one. So we can actually do this completely independent of the total number of keywords, and we can do this in a dead zone style of algorithms as well. Again, a different family of algorithms that's invited by that. And we can also do two-dimensional or multi-dimensional pattern matching. Now, unfortunately, this is not the really interesting two-dimensional pattern matching that, for example, people working in security and image processing would like to do. So if you're doing facial recognition, you'd like to be able to do pattern matching that allows for scaling and rotation and shading and various really interesting security problems like that. But this is the more rudimentary problem where there's a rectangular body of text, and we're looking for all occurrences of a pattern within that without rotation and without scaling, as I say. But it turns out to have interesting applications within manufacturing, for example, manufacturing of silicon chips and checking of printed circuit boards are two of the applications. And we'd like to be able to position the pattern right in the middle of the input. And we already know that we could proceed to do a match row-wise and see if there's actually an occurrence there. We have some notion of a dead zone which appears surrounding that, and that dead zone is kind of a zone in which it doesn't make any sense to then go and move the pattern, because we already know, based on what we've discovered, that there's no possible way of the pattern occurring there. And we'd then like to make our next attempt somewhere outside of that dead zone, and we'd even further like to actually restrict that dead zone in a kind of safe way to an inscribed rectangle. And in other words, remove this funny looking polygon on the outside and just say we restrict ourselves to a dead zone that looks beautiful like that. And this then leads to a family of algorithms that also hasn't been seen before. So some of the algorithms leading up to this had been explored in quite some detail since the 1980s, and in relation to the normal stringological algorithms. But once we have a way of looking at it like this, we could also do a kind of bisection of the remaining portions of the plane. And there we can see we have 8 regions in which it makes sense to go and look for other potential matches. And this allows for all kinds of parallelism. So we could then go and do our pattern matching, one by one through all of those regions, but we could actually get a lot of traction just by going straight to doing all 8 of them simultaneously by splitting up this region and setting a process or a thread looking at this region, this region, this region, and so on. And we have this then 8-way parallelism for the next step. And of course, it shouldn't surprise you that once we've had one thread examining this, there will be another dead zone surrounding this, and this region here will then itself be divided in 8 further regions that are then to be examined until, of course, it's arrived at empty regions, and then we know that that's a dead thread or it's been completely exhausted. So, other areas that we've explored this, let me close off by zipping through this, but I think those of you that have dug into this a little bit before probably know that we've explored tree algorithms for this, finite automata, construction, minimization. So as I say, some very, very old techniques in this as well. Time doesn't allow me to discuss the following, but this is what actually underlies this work. So we're not only interested in inventing new algorithms, we're actually interested in coming up with implementations of these algorithms, toolkits, or libraries, I think is probably the more honest way of naming them. But we have a methodology of mapping the underlying taxonomy directly down to the structure of a library, either the class hierarchy or some other way of sharing code. Because as you can see in the taxonomy, we have some very significant areas in which there's sharing of the underlying structures. So the taxonomy structure itself gets mapped rather directly to certain elements within a UML diagram, which then drives the choice of various design patterns and leads directly to a final implementation. So let me close off then with the conclusions. I think one of the things that I hope is reasonably clear is that if you do this diligently and of course with correct tool support, then CBC always comes up with a correct algorithm. One of the other things is that the correctness proof is not something that's done separately from the algorithm. It's actually integral with deriving the algorithm as we go. Personally, and also this is my co-author Derek Curry, who some of you have met as well, and many of us working in CBC recognize that no one's really in real life going to use full-blown CBC for the long way of doing an algorithm. Everyone's going to use something much lighter than this, and this is also one of the reasons why tool support should be there. Once we have multiple algorithms in the same derivation framework, we actually essentially have a taxonomy, and then we have all of the potential openings for discovering gaps in the taxonomy, and as I say, for coming up with new algorithms as well. Lastly, as you can imagine, and I don't just say this from the perspective of selling books, but we firmly believe that whichever framework you use, CBC should of course be something that's taught at some point in the curriculum. And in some universities, of course, it's been abandoned, and people go back to a more, let's say, hacking-oriented way of coming up with the code, but at least it still has a place within formal methods, and hopefully within the pedagogics of basic algorithms. The future work is something that quite excites me. I think one of the things that I didn't talk about now today is lattices, formal concept analysis, and algorithms surrounding that. But I think one of the ways to proceed is not only to use the CBC that I've shown today, but for example, you could have CBC and a set of calculi or a calculus for manipulating CBC programs for a particular domain-specific language. So you could do this, for example, for MATLAB or Maple or Mathematica, but you could do it for GP, so graph programming. So I think one of the ideal things would be to take GP or GP2, and which already has a proper specification of the programming language, and you could then recast many of these graph algorithms as GP programs and actually derive them in a way that appeals to the intuition at each step about how the graph is being manipulated, as opposed to what most of us do, and I've been involved a little bit in FCA algorithms, but most of us appeal to some rather heavy notational frameworks to express the graphs. And it might be more appealing if there's a visual framework in which to express the nodes, which nodes get added when, and the code that triggers the adding of a node or removal of a node. So I think that could be in particular useful. And then the last one is something that I've said many times so far, and luckily there's several groups now working on this kind of thing, and hopefully this breathes some new life into realistically using CBC. And there you go with some references. Obviously many self-references here, and I don't mean to only push our own work. As I said, this is actually very much built on the shoulders of giants, and it's lucky for us that we've been able to take this further. So thanks very much for your attention beyond time.
Thank you. Any questions?
How this correctness is by construction can be related to optimality by construction.
Ah, okay. I'm very glad you say that. Yeah.
Designers are usually interested in optimal.
Right. So actually, it's very interesting you say that, because there are a couple of potential things that come into this. Now, most CBC work has until now been purely correctness oriented, and I think it's maybe a flaw to say that we only think about correctness. A couple of other things that you could think about is interweaving each of the refinement steps with co-developing the complexity argument. Okay, so complexity arguments are very often built after the fact through very, very impressive analysis, but you could co-develop that entire argumentation as you go. And furthermore, you could actually introduce notions of optimality of the end result as you actually derive the algorithm, or notions of near optimality, or notions of approximate optimality through each of these derivation steps. So I've never once seen someone proceed in this direction, but there's absolutely no reason why it shouldn't be done. And in fact, something that's very much in the same area would be to say, you know, we're deriving slightly more applied algorithms related to cryptography or protocols or information flow, and we'd like to co-develop not only the argumentation and the assertions about the specification, but also about information leakage. So you actually co-develop an algorithm that's not only correct by construction, but secure by construction, in terms of some notion of information theoretic information leakage. So these are very interesting notions, and very topical notions if you look at optimality, parameterized complexity. On the other side, you look at information theory and development of cryptography, development of compression algorithms. But as far as I know, no one's making any progress, or no one's even attempting to make progress in these kind of constructive techniques applied to this. I think it's a fantastically rich area for someone to do some work.
So when you speak about correctness, then it should be correctness with respect to some semantics. So how do you describe the domain? Because when you write sorted, it is nothing. Yes? And actually there was mistake, because you shouldn't write unsorted for the second part. It should be just true, of course.
Yeah. I'm very glad you said both of those things. So just to quickly answer your second comment first, you're completely right that depiction of everything from I to the end of the array, I should never have written unsorted, because you simply don't want to say anything about it. It could actually be sorted, as you imply. So that was a piece of pedagogic trickery that I used. But you're absolutely right. It's not correct. And furthermore, your other comment is actually a very important one. And this, on the one side, I would say, is where Derek, so my co-author on the book, but also collaborator of many of us over some years. But Derek and I have been thinking for some time that on the one side, you would like to encourage uptake of CBC. By somehow appealing to intuition or a common library of definitions related to sortedness. But on the other side, at the same time, I admit that you need the formalism, but furthermore, you would actually like to have a proper tool, either an Eclipse plugin, as I said earlier, or something else that's connected to an automated theorem prover that can do some of this. And the moment you introduce something like an automated theorem prover, of course, then you need a properly formalized definition of sortedness. And so that's an interesting other problem. And part of these slides actually come from some work with colleagues. And we spent a little bit of time actually trying to use automated tools to do this. And we ran into exactly what you say, that we need this thorough underpinning. So now we're at a kind of philosophical crossroads where on the one side, for the purposes of quickly coming up with new algorithms, or at least playing and enjoying the invention of algorithms, you'd like to appeal to this kind of intuition that I did here, which is cheating. Or you'd like to have a rich enough library where we agree commonly what sortedness means. And on the other side, you'd like to have a fully populated palette of already partially executed automated proofs that you could do it more formally. So semantically, I've left all of that out right now. And so that should then be, some underlying semantics related to the guarded command language. And there things even become a little bit more tricky because this was an argument between Dijkstra and many logicians a long time ago. And that is the first order predicate logic as it's used in the guarded commands by Dijkstra and then Gries and us and so on. Exactly. Exactly.
Then maybe just because you are doing such nice things, but then why to speak about correctness? Because then you are cheating actually. And then so just to say that you give taxonomy for algorithms, just some insights for intuition to find something new. But when you say correctness, then so just people say, well, so just you're not correct.
Yeah, I certainly.
We do not believe you.
Yeah. I certainly concede that. Of course, you're correct about the notion of correctness here. I would say that we need to keep in perspective where these things should belong. On the one side, if these things should belong as formalized archives of proper correctness of algorithms, then there's more machinery required, as you say. If it's something to appeal to pedagogics and as a roadmap for algorithms, perhaps it needs a different name from being correctness by construction, or perhaps it should be just viewed as a roadmap and introduction to the algorithms. And there's somehow a spectrum of heaviness of machinery from here to there, where this appeals to more intuition, and this, of course, is entirely formalized. So there's also, I think, a desire to find, something in the spectrum that's maybe not overly formalistic, because it realistically, I think, was one of the things that prevented Dijkstra's work from being commonly used. I think we can say that no curriculum worldwide nowadays uses CBC in a very strict fashion. And it's because students aren't interested, but it's also very formalized. And from a scientific perspective, it should be formalized, but from the roadmap and survey and pedagogic side, it probably shouldn't be formalized, because it seems to somehow be the obstacle of uptake, or obstacle towards excitement in doing things this way. But I take your point absolutely.
Any other questions? Yeah.
In your two examples, you prove correctness of some simple sorting algorithm by a for loop and then choosing an invariant. Why not by induction? It seems like easier formally and just for teaching. Like I teach some algorithms in computational complexity. I always default to induction because there are less variables and it's more. It's easier to formalize. Yeah. Okay. Well, I mean, I must confess, I'd have to go and do some experiments to convince myself. As you can imagine, I've grown up to a large extent in this formalism for showing this, but I'm open to having a look at this in a very different way. And
but have you ever worked with automated assistant theorem provers? I once worked with Isabel, and everything was by induction. And I really liked this.
Right. Yeah, so I haven't in particular, but and somehow marrying this with CBC is already some of the effort that we're on with the authors of the Key tool, for example. But there's also, as you say, quite a difference in the way of thinking. So it's not so clear where the middle ground is, and a lot of CBC is, of course, simply design choice. We could have made many other design choices here and ways of structuring the argumentation that may have been more suitable pedagogically, but also more suitable for using a theorem prover. And so I shouldn't be too pushy with the version that I've shown you here. I think there's a very, very broad spectrum of possibilities of how to do it.
Thank you.
Thank you. Thanks.